There are several possible causes for induced voltage affecting the operation of variable frequency drives, particularly the stop function. Electromagnetic interference, or EMI, from nearby equipment or wiring can induce voltages in both control and load wires. Capacitive coupling, where parallel runs of control and load wires act as a capacitor, allows voltage transfer between circuits. Inductive coupling occurs when magnetic fields generated by load currents in the power wires induce voltages in the control wires. Several reasons could explain why this problem has only recently arisen. The addition of new equipment or wiring in the vicinity could have altered the electrical environment and increased EMI. Insulation or shielding on the wires may have degraded over time, leading to increased voltage leakage. Inadequate or poor grounding can provide a path for induced voltages to enter the control circuits. Loose connections in the wiring or terminals can create high resistance points that can induce voltages. Several solutions can be implemented. The most effective is separating the control and load wires into different conduits or using shielded cables. This reduces EMI and capacitive coupling. Installing EMI filters on the drive inputs can block high-frequency interference. Twisting the control wires together or using shielded cables reduces inductive coupling. Ensuring all equipment and wiring are properly grounded provides a low-resistance path for induced voltages. All connections in the wiring and terminals should be tightened to minimize voltage drop and potential induction. Furthermore, determine if any recent changes have occurred in the electrical system that could have contributed to the problem. Consult with an electrical engineer or qualified technician for assistance in troubleshooting and implementing solutions. Consider using an oscilloscope to verify the presence and magnitude of induced voltages on the control wires. When diagnosing the issue of drives not stopping, it is important to consider each of the previously mentioned factors. Electromagnetic interference is a common culprit, especially in environments with a high concentration of electrical equipment. Sources of EMI can include other drives, motors, switching power supplies, and even lighting systems. This interference can manifest as high-frequency noise that is superimposed on the control signals, potentially triggering or inhibiting certain functions of the drive, such as the stop command. Capacitive coupling arises when two conductors are in close proximity, separated by an insulating material, forming a capacitor. In this scenario, the control and load wires running in parallel act as such, allowing alternating current voltages to pass from one circuit to another. The amount of voltage transferred depends on the frequency of the signal, the length of the parallel run, and the distance between the wires. Inductive coupling, on the other hand, results from the magnetic field generated by current flowing through a conductor. This magnetic field can induce a voltage in a nearby conductor, particularly if the conductors are arranged in a coil or parallel configuration. The magnitude of the induced voltage is proportional to the current flowing through the first conductor, the frequency of the current, and the mutual inductance between the two conductors. The fact that the problem has surfaced recently, despite the system having been in operation for years, suggests that something has changed in the electrical environment or the system itself. Consider the potential for changes in equipment. A new piece of machinery with high harmonic content might have been added to the facility, injecting noise into the power distribution system. A modification to the building's wiring, like adding a new branch circuit, could have inadvertently created a ground loop or increased the proximity of control and power wires. Over time, the insulation on the wires can degrade due to heat, moisture, or chemical exposure. This degradation reduces the insulation resistance, making the wires more susceptible to capacitive and inductive coupling. Additionally, the shielding on shielded cables can lose its effectiveness if it becomes damaged or corroded. A robust grounding system is essential for minimizing the effects of EMI and induced voltages. Grounding provides a low impedance path for unwanted currents to flow back to the source, preventing them from circulating through sensitive control circuits. If the grounding system is compromised due to corrosion, loose connections, or improper installation, it can become a source of noise and instability. Loose connections are a common cause of electrical problems, including induced voltage issues. A loose connection creates a high resistance point in the circuit, which can act as a source of EMI and can also exacerbate the effects of capacitive and inductive coupling. When current flows through a loose connection, it generates heat, which further degrades the connection and increases the resistance. Addressing these issues requires a systematic approach. Physical separation of control and load wires is paramount. Running them in separate conduits eliminates both capacitive and inductive coupling. If this is not feasible, consider using shielded cables for the control wires. The shield acts as a barrier, preventing external electromagnetic fields from inducing voltages in the signal conductors. It is important to properly ground the shield at one end only to avoid creating a ground loop. EMI filters are designed to attenuate high-frequency noise on power lines and signal cables. They typically consist of inductors and capacitors that form a low-pass filter, blocking high-frequency signals while allowing low-frequency signals to pass through. Installing EMI filters at the inputs of the drives can effectively reduce the amount of noise that reaches the control circuitry. Twisting the control wires together cancels out the magnetic fields generated by each wire, reducing inductive coupling. Shielded cables provide even better protection, as the shield absorbs and dissipates the electromagnetic energy. A thorough review of the grounding system is crucial. Ensure that all equipment is properly grounded to a common ground point. Use appropriately sized grounding conductors and make sure that all connections are clean and tight. Consider using a dedicated grounding conductor for the control circuits to minimize noise. Inspect all connections in the wiring and terminals for looseness, corrosion, or damage. Tighten all connections to the proper torque specifications. Replace any damaged or corroded connectors. An oscilloscope is an invaluable tool for diagnosing induced voltage problems. It allows you to visualize the waveforms of the control signals and identify the presence of noise or distortion. By measuring the amplitude and frequency of the induced voltages, you can determine the source of the interference and the effectiveness of your mitigation efforts. Begin by examining the control wires with an oscilloscope to identify the presence and characteristics of the induced voltage. Note the amplitude, frequency, and waveform of the noise. Compare these measurements to those taken at other points in the system, such as the power lines and ground conductors. This can help you to pinpoint the source of the interference. Once you have identified the source of the interference, you can begin to implement mitigation strategies. Start with the simplest and most cost-effective solutions, such as separating the control and load wires or tightening loose connections. After implementing each solution, use the oscilloscope to verify its effectiveness. Keep in mind that induced voltage problems can be complex and may require a combination of solutions to resolve. If you are unable to resolve the issue on your own, it is best to consult with an experienced electrical engineer or technician. Remember that changes in equipment, wiring degradation, and grounding issues are all possible reasons the problem has arisen. Separate the control and load wires, install EMI filters, use twisting or shielding, improve grounding, and check the connections. An oscilloscope can be useful for verifying the presence of induced voltages.